Okay, Unit 6 review starting from number 9. So this picture is showing the exponential function 2 to the x, and if you look at the graph that they are, the equation of the graph they want you to make, the two things that are different are the subtraction of 4 and the subtraction of 5. So the 4 is going to move your graph to the right 4, and the 5 is going to move your graph down 5. So you notice that in my work, one thing I did was to locate some key points on the parent function, the 2 to the x. So by key points, I mean ones that cross at grid lines. I could think about 2 to the first, 2 to the second, 2 to the third, right? Find those kinds of points on my graph. And then I took each of them and moved them 4 to the right, 5 down. The parent function has a horizontal asymptote of the x-axis. Moving a horizontal line 4 to the right doesn't change it one bit, but moving it down 5 does. So my new horizontal asymptote is at y equals -5. For question 10, I have e to the x. It might be a little bit harder for you to think about what your key points are on e to the x, but it certainly goes through the point 0, 1. And then if you put in 1, you get out the number e, and e is about 2.7. So this point is the other one that I personally thought about. The rest of the numbers are there aren't like nice, clean, like crossing a grid line kinds of points on this, so which makes it a little bit harder. I'm just going to show you my work for the sake of not talking to you forever. But you can see that I marked those 2 points in black ink on this slide. And then because I am looking at the natural log graph, not an e to the something, I know that I want to think about the inverse. So in blue, I have y equals natural log of x. And so blue on my graph, I just took the point 0, 1, made it 1, 0. I took the point 1, e, I made it e, 1. And then I know that this shape has to be that's the kind of shape I'd get if I reflected the like kind of pinkish curve over the line y equals x. And then that equation is what I'm going to think of as being like my parent graph, that blue graph. And if you compare my blue equation up here to the one I'm writing a box around right now, then I know I need to move 4 to the left and down 2. So I took those 2 points, I moved them 4 to the left and down. Wait, did I remember the down part? I don't think I did. I just moved them 4 to the left. Sorry, guys. So 4 to the left and then down 2 is what I was supposed to do. And then down 1, 2. Sorry about that. And so the green is not correct, but the purple is, okay? I'm really sorry. I'm glad I was talking. It caught my mistake. All right, question number 11 says to use properties of logs to rewrite and find exact values. So and it says try not to use your calculator. We're just trying to encourage you to grow as a mathematician. If you have to use your calculator, you have to, but we'd rather you didn't. So for instance, on this one, I want to be thinking about this is going to be some value. That's what I'm trying to find. And so 4 to the x equals 8. And I want to think about, can these be written with the same base? And they can. 4 is 2 squared. And so I have 2 squared raised to the x power. And then this is 2 to the third. And remember, when you have a power to a power, you're multiplying. So I'd have 2 times x would have to be the same as 3, since these are both the same base now. So x would be 1.5 or 3/2. In the next question, I could rewrite this using properties of logs. So if I have multiplication, I can write those as logs that are added together. And then I can use this property of logs that says the 6 can come down in front. So I'd have natural log of 5 plus 6 times natural log of e. And the natural log of e is 1. 6 times 1 is still just 6. So the next question, I would say, like, write this as being equal to x, and then 3 to the x equals 9. And hopefully you can just think about that and know that it's 3 to the second that equals 9. In the next question, I would, again, think about this as being x. So 2 to the x equals, and I'm going to try to do another step at the same time. 8 is the same as 2 to the third, and a fourth root is 1 to the 1/4 power. So if you look here, this has equal, and it has the same base now that I rewrote it. So that means that x has to be 3/4. For e, write this as equal to x, and 4 to the x would equal, and I'm going to try to do a little move here. 16 is 4 squared, and then I had another 2 that was in the question. And so I wrote these both with the same base. So now I can see that x would have to equal this exponent of 4. Over here, this question's not possible. Okay, if you think about a log curve, natural log or log base 2 or log whatever, it only has a domain on the positive half of the coordinate plane. You can't take a log of a negative, so this is a no solution. Here, e to a power and natural log are going to undo each other. Those are inverses. Here, I could rewrite this. I think that's useful as e to the negative 1/2, right? Square root is a 1/2, and in the denominator makes it negative. So this would just be negative 1/2. And here, same kind of idea. These two, as the last question, I didn't actually say it, but I was thinking about that exponent coming down in front. Samesies here. And then natural log of e is 1. So this is 2 times 1 plus 5 times 1, which equals 7. So here's a maybe nicer looking slide. Seriously, my handwriting when I'm writing in real time is such a mess, but I can actually be neat if I take my time. Right? So if you could just want to take a look at those solutions, you certainly may. Okay, number 12. 12 has a lot. Okay, so this said use the properties of logarithms to expand the expression as a sum, difference, or a constant multiple of logs. So we're trying to expand or spread out these pieces. I will tell you, as a calculus teacher, this is something we use quite a lot in calculus life because it's nicer in math to have little teeny bits to work on instead of big globby globs. Those are very technical terms, teeny bits and globby globs, but truth. Okay, so multiplication with a log you can write as addition. Here I'm going to use this 4 and bring that down in front. Here I'm going to see that I'm dividing, and that is the same as subtracting when I have a log. And then this part is saying what exponent do I put on a 5 to get 5? And that's just 1. So here's my nicer handwriting version. All right, same idea here. We're going to think about this square root as being to the 1/2 power. We're going to, I'll come back to the rest of that. We're going to split this apart and bring the 2 down in front. And for f, we're going to think of multiplication, which will become addition, and the 2 will come down in front. So I'm just going to show you my work here. So on D, 1/2 comes down in front as a multiplier, and that's as good as it gets. Here, all of the multiplication became addition because these are logs, and then the exponent can come down in front as a multiplier. In F, the multiplication becomes addition, and again, the 2 comes down in front. Okay, the next few, these all have radicals, and so you need to bear in mind the things that we learned in the previous unit about radicals being able to be rewritten as exponents. Right, so that, for instance, or I didn't finish that question, don't worry. Or I could write this, right, as my first step on H, or for here, x squared, and then y to the 1/2, and z to the 1/2, right, would be a possible beginning point. So to show you my complete work here, the division is the subtraction. And then that 1/2 power that I had can come down in front. Here, right, the cube root is to the 1/3 power. You can write that separately on each piece, and then you could subtract. And it doesn't matter if you leave, if you leave on question H, if you leave the 1/3 on each part, or if you factor the 1/3 out. It kind of depends what order you think of things in. Over here, all of these exponents end up coming down in front as multipliers of their individual pieces. So you should have a 2 with your natural log of x. You should have a 1/2 with your natural log of y. And then this is subtraction because the part that had the z was in the bottom, right? It was in the denominator. So that has to have a subtraction because it was divided. And that's how the log properties work. So when I had the division, that becomes a subtraction in terms of the natural log properties, or log properties, I should say. All right, I think I'm going to pause here and come back to you with the next video.